Okay, so hello everyone and welcome to this session. So my name is Fernando Ramos. I am an associate professor at the IST University of Lisbon, and I'm here very fortunate to present Rafael Guimarães. He's going to present his work on multipath stateless source routing. So Rafael is an associate professor in the Department of Information Systems at the Instituto Federal do Espírito Santo in Brazil. So he got his PhD from the University Federal do Espírito Santo in 2021. So he also worked as research associate in the High Performance Networks Group at the University of Bristol. And he was involved in many European projects. His recent research interests include SDN, network softwareization, network security, etc. So, the stage is yours, Rafael.
Thank you, Fernando. Thank you, everyone. Um, Hi, everyone. My name is Rafael Guimarães, and I'm here to present our work named M-PolKA. Is a multipath dynamic and exploit multipath stateless source routing for programmable data planes. So, just showing us where we are now. So, our institution here is located in Espirito Santo, in Brazil. And I'm associate professor in the Federal Institute of Espírito Santo, and my campus here in the middle. And I'm a collaborator at the Federal University of Espírito Santo as well, which main campus is located in the capital of our state. So our research group, NERDS, is dedicated to innovate to innovating network systems, especially in the area of software-defined networks. And we try to embrace the whole innovation cycle of designing, prototyping, validating, publishing, including commercial applications of our ideas with startups. So in this presentation, I will show the key insights of our proposal. So the motivation, proposal, designs. I will clarify with some prototypes, conclusion, and ongoing applications. So start with the motivation. In the recent years, programmable network device have enabled the deployment of innovative protocols. So the traditional solutions of forward packets based on table lookup, for example, has some bottlenecks because it requires a large number of network states, which impacts the network scalability and the limited token availability. So it impacts the granularity in the limited capacity of the switch tables, and the latency to configure path impacts the agility of forward of the solutions. Um, as an alternative to tackle this problem, we have source routing. So the source specifies a path, and that adds a source label to the packet header. So in this approach, the source node adds a route label in the packet header to specify an end-to-end path. So traditional way to represent source routing is a list-based source routing solutions. So which the path is a list of ports and address. So each node performs POP operations. So having this in mind, the forwarding operation as a POP of the first element. So imagine that the source sends a multicast path that will be simultaneously received by the destination 1 and destination 2. So the route A determines basically that the C and D are the egress routers. So parsing a sequential list of hopes does not allow the represent multipath in this solution. So we have uh, this problem when we are talking about list-based source routing. So in this case, considering this motivation, our proposal with M-PolKA is to design a source routing approach that simultaneously meets the following requirements. Needs to be topology agnostic. We don't have tables in the core, and we don't have state in the packets. Should be implementable in programmable switches. We have an encoded path, a fixed header, and you can express multiple paths. So M-PolKA, this idea M-PolKA, a multipath polynomial key-based architecture, is to explore this residual number system and the Chinese reminder theorem by performing the forwarding as an arithmetic operation. That is the remainder of the division. So in this way, the path is encoded in the route label, and the next hop is decoded by each node using its own key. So this key means its own node ID. So explaining using a timeline the evolution of our proposal, in 2020, we proposed PolKA that explore polynomial RNS arithmetic and a way to enable its implementation programmable switches by reusing CRC hardware. So after that, uh, exploring these features by using this approach, in this case, multipath forwarding capabilities. So in 2020, we have this solution was focused only in a single path, and in 2022, we have a proposal of M-PolKA focusing on only for multiple paths. So in 2021, we received a Google Research Scholar Award, and in 2022, we received the Intel Connectivity Research Grant that will be possible, that we got basically 3 Tofino switches in this case. So first of all, I will explain the design of M-PolKA, how M-PolKA works. So the architecture basically relies on three polynomials. So we have a route ID, we have a node ID, and we have the transmission state. The route ID identifies is an identifier that was calculated by using the CRT. And the node ID identify each core node. So in translating in a polynomial way is a reducible polynomial. And the transmission state is identified the transmission state of each node. So the forwarding uses a mod operation between the route ID and node ID to define the transmission state in the final. So uh, in this slide, I will show the simple example how M-PolKA works. So considering the source and destination, they are connected to the edge switches, which are connected to the core fabric. So in a network configuration phase, the controller initially assigns the node ID to each core switch, which means different reducible polynomials. So in this case, we use the polynomials of degree 5. For example, in the first switches, we have the 100101. Um, so, and the ports are represented as a binary polynomial marked by its position in the transmission state. For example, the port 1 is represented by the bit 1 in the binary polynomial as 0001 and port 2 as a 0010. So for example, if I want to split the traffic or load balance the traffic to many ports, in this case, port 2 and port 3, the binary polynomial is represented by 0110. That marks the position 2 and 3 in this polynomial. Then the controller is responsible to choosing the path for the flows. For the path here is represented by a set of switches in red in this picture, and their transmission state is represented in blue. In this example, port 10 for the switch 1, port 0110 for switch 2, and 010 for both switch 3 and switch 4. So, well, the information is in red and blue, and the controller is able to calculate the route ID by using the CRT, the Chinese reminder theorem. For our example, the calculated route ID is in green. So if we have the route ID, the mod operation between the route ID and node ID, we have the transmission state and the final on each node. So after calculating the route ID, the controller installs the flows entries at the edge to add or remove the route label. So when the packet arrives, the ingress node adds the route ID into the packet, and each node performs a single mod operation of the route ID of the packet by its node ID to discover the transmission state. So just to give you a little brief about how we have implemented the CRC custom and P4 switches, on the left side is how we set the reducible polynomial and use the CRC custom in the VMV2. And on the right is how we set and use GRC custom using the Tofino architecture. So in BMV2, we are able only to set the node ID via command line, whereas in Tofino switches, we set the node ID via a gRPC interface. So using Tofino switch, we achieved about 1000 gigabits per second of throughput, and we had the same performance compared to other forwarding methods. And it was a publication that we did comparing PolKA and other kind of forwarding methods. So at the first node, the route ID is divided by the node ID, which gives the remainder 10. So in the transmission state, the switch steer the traffic only to port 2. And just an small example how we have implemented the board operation BMV2, and a small example how we identify that that port or ports belongs to the transmission state. So at the second, doing the same operation, and the remainder of the division is equal 0110, and the transmission state, we have to steer the traffic to the port 2 and port 3. So in the third node, doing the same operation, the remainder of the division is 010. So the transmission state, we have to steer the traffic to port 2, and the same happens in the switch 4. So the division between node ID and route ID is equal 010, and we steer the traffic to port 2. So finally, the egress node removes the node route ID, and the packet is delivered to the application in a transparent manner. So as a proof of concept of our approach, we have, we have developed some prototypes. So it's important to note that we deploy our prototype in Andean P4 lab to compare our P4 data plane implementation with list-based and table-based approaches. So the preliminary results were published in our ONDM conference paper, uh, as in preliminary paper, and we have some integration with the REP project. So this integration with PolKA and M-PolKA in the REP project, we have conducted, we aim to provide our open routing solutions. So in the REP project, the P4 data plane supports BMV2, Tofino targets, and the PDK, and their control plane is based on free router, which is free and open source router process that can be used for anyone to, if you want to implement a new protocol or a new forwarding method, is really uh, free to different kind of forwarding methods. So it also offers the first open implementation of segmented routing. So the PolKA is the first non-standard protocol being implemented in this project, the REP project. We thanks Kisaba Mate and Frederick Lu that helped us a lot with this implementation. So to develop the PolKA control plane, we reuse standard distributed protocols already running in the RARE and the free router. For example, we reused available topology information from link state routing protocols when defining the PolKA and M-PolKA tunnels. So in this implementation, the header of our product has fixed length header that we can use different encapsulation during the transmissions. So in this example, the route ID that we have defined as 128 bits. So in this emulating experience showing how we can configure M-PolKA using free router and a different solution for a control plane, we explore how to create and tunnels for multiple paths, mimicking a little bit the rare test bed. So we have here Rio, Amsterdam, Poznan, and Budapest, Frankfurt, and Geneva, mimicking their rare test bed. And we would like to define tunnels between Rio and Geneva. So the paths are defined in red for short and long path and longest path. And so basically when the packets arrive in Amsterdam, the switch duplicates the packets. So one is steered through Poznan, Budapest, this is longest path. And the second one is steered to Frankfurt, that is shortest path. So the user define a POC in a node and assign the node index. For example, here, the node index 11. So to facilitate the settings of Node ID to all interface, we have the functionality templates. So we define a template that is a Node ID is 11 for this router and Rio, and we use the same template to our interface. So after that, the node assign the node ID index, which is mapped to a node ID polynomials. And when the tuner is rated, the free router automatically calculates the route ID for a specific tunnel. And how can free router calculate the route ID? So when you define the tunnel, that is very easy. You just need to address the nodes in the path. In this example, to duplicate the packets in Amsterdam, we have to specify multiple next hopes that the packets have to be sent. So for that, the node Amsterdam steers the traffic to Frankfurt in red, and also a copy to Poznan in purple, which is the node 2020-22 and 2020-24 respectively. So this is how we use M-PolKA by using free router. So we also start organizing a public GitHub with the reference and codes. And at the moment, we have basic tutorials on how to enable PolKA and M-PolKA testing in Mininet and free router. We also provide a Wireshark dissector, and we are preparing more tutorials for Tofino and BDK. Uh, so the conclusion of our work is we demonstrated that M-PolKA can be deployed in high programmable switches and with the reuse of CRC hardware, and our performance is equivalent to traditional approaches. So, but M-PolKA can enable a new um, range of complex network applications. So the potential in also have the potential uh, for any other application that we didn't think at the time. So the current work that we are that is ongoing work that we are in collaboration with the red team is a full of P4 implementation and a compto plane dependability and applications. So some ongoing applications in this example, a multicast application may need to configure a branch in a multicast tree because it wants to react to a failure or to guarantee a QoS requirements when there is some concurrence, or even to add a new client in this case. So imagine that we want to change the path to deliver the content to E and include a new client G. So have the same content, but I need to add a new, I need to send the same content to a different client that just arrived. And so at the beginning, the edge is configured with the blue route ID on the left, and using M-PolKA, the controller modify a single entry at the edge, and the packet will be tagged with the new purple route ID. So we can provide an agile modification of the branches. So it's just a matter of changing everything at the edge. We don't need to modify the states during the all switches at the core. So uh, thank you, thank you for everyone for this opportunity. Any question?
So thank you. I would just say that I enjoyed very much your presentation and the work. I think the technique seems quite clever. I do have some questions. Also, congrats on the awards. Quite impressive. So first, I would question a question just about the motivation of the work. So I'm not an expert on this, but as far as I understand, segment routing when it appeared, so the idea was kind of reusing the MPLS routers that we had, right, in order to do some clever traffic engineering. But in this case, what you're saying is that I guess we cannot reuse the MPLS routers here because you're doing this in a programmable data plane. So why segment routing in the first place?
Yeah, because the first things that we have choose the segment routing is because we don't need to keep the states in the core, in the whole core to change some kind of path. So segment routing, the paths is automatically added at the source. So you don't need to, the controller don't need to change or need to have a kind of controller in the core if you want to change some path in the end-to-end communication. So thinking on that, we have this, we have thought a lot because about segment source routing, because it's a kind of way that we don't need to take care of the whole state in the core, and then need to take care at the edge modification to define a new path or to change the path on this case. So starting this with this working with source routing, no source routing brings many um, uh, problems in their implementations, and we try to overcome these. We thought that okay, we can overcome these limitations with multipath, um, working with multipath. How can we do this? So this RNS and CRT is we don't need to strictly create a list, and needs to be linked between them. The encoded paths can that it doesn't need to be connected. So we encode everything in the path, and then switch extract their information automatically and see what would be the action that I have to do for the package to one port or many ports in this case. So
Okay, got it. Yeah, thank you. So the second thing was, so this is maybe just a clarification, because in the end you were saying, what our goals is not to have like state in the, like no tables in the core and no state in packets, but effectively you have state in packets, right? Because you have the root ID.
yes, but
what did you mean by no state in packets?
So we have talked about it, a lot about that, because when we brought this kind of stateless is a kind of which part of my network I have state. I have state in the edge only, but I don't have state in the core. So I don't need to change anything in the core to pack to be steered to one of many ports. But I still need to keep some state at the edge. So there's one point of changing that I have to keep, one point of state that I have to keep. The controller needs to maintain at the time, but in the core, I don't need it. So I don't need
Sure.
to.
My question was related to state in packets, because I think you also mentioned that you don't need state in packets, but you need state in packets, right?
Yes,
There is
yes.
a
But
overhead, let's say, in the packet, because you need the
yeah.
root ID.
Yes, but yeah, yeah. You need, because you don't need because you don't change the root ID in the packet, so you don't need to change the state during the forwarding process in the core. So as a list based, what we meant at that time, when you have a list based solution for source routing, you need to do pop operation at each hop that you're passing, and you change the state in the package. So,
Okay.
but by using M-PolKA and M-PolKA, you don't need to change it. The route ID keeps as it is during the whole path in the core. So you don't need to
Okay.
change it. So the state doesn't change in the package. So the packets change at the edge, but it keeps during the whole process at the core. So that's the argument
Yeah. Now it's
that
clarified. Now I
we.
understand. Okay, perfect. Cool. So now another question on how to run this in the Tofino, right? I think so. You were able to. So you're using an Intel Tofino. So I guess the program is compiling and running there. So my question was, so you mean that the operations that you have to do, like in the CRC, like those shifts and XOR, etc. So it's like they fit into a single action, like in a single stage, or do you spread them across multiple stages?
What do you mean stage in Tofino? Because Tofino, you have, for example, the ingress and the egress stages and so on.
Yeah, but usually when you have complex operations, you have, like in the ingress, you have multiple tables or stages, match action tables, right? And
Okay.
you have limitations on the actions that you can run, but I guess you can run. Can you run all these like in a single stage?
Yeah, sure. We did it
Okay.
in the ingress stage. So we create like an action, and this is all the CRC process is just in one action processing at the ingress stage.
Okay.
So and then
And then
Tofino as well.
sure,
And then
sure.
Tofino
Yeah,
as
my
well.
question was if whether the Tofino is breaking that into multiple stages or not. like the Tofino
No,
compiler?
no, in Tofino we did it only the ingress stage as well. So in the Tofino, because when we our first implementation Tofino, we every SCRC was performing in the ingress process only. It was a basic implementation that only we got the output port or the multiple port that I have to steer. But by using free routing needs to maintain a lot of legacy protocols and integration of these all the legacy MPLS and so on, and they work during this not the CRC but the forwarding process during many stages. But you can use only one stage to calculate the CRC, no problem. Only the ingress part. I don't know if I answered your question, Fernando.
Yeah. I think so. Okay, so my last question is has to do with the like the dynamics of the network. I'm wondering what do you need to do when like a switch, like the topology changes, right? The switch files or some connections disappear. How does this affect the process?
So that was one of the begging questions with M-PolKA, because before we try to analyze when you have a link failure, you change your topology, and you need some protocol to define, oh, we have changed my topology, so I have to calculate my route ID because I need to cross a different path. Even I can use, for example, protect paths automatically in my route ID, because artificially I can add switches even if the switches are not in the path. So in case of you have some failure, you can just use a different switches and we will calculate because it's encoded in the route ID. But so we work with, for example, we start using a small control plane to deal with this kind of problem. And with free router, we are using legacy protocols for link stage, for example, OSPF, and integrated with M-PolKA and M-PolKA. So if you have a failure, the topologies change, the free router automatically calculates the new route ID for this end-to-end communication and generate a new and add this at the edge. So because free router has this integration with the legacy protocols to keep this communication with the other switches, other industry vendors, and that's it. So but this is this control plane approach for only M-PolKA and M-PolKA is still an ongoing effort at trying to analyze it, and we try to keep this legacy compatibility with by using free router. So because free router has MPLS, has segment route implementation, and OSPF, BGP, and all the legacy protocols, and we can integrate it with M-PolKA and M-PolKA. That's a good thing that we got with this collaboration with the red team. And the code is totally open source, so anyone can use and can collaborate or add some stuff or new protocols that they have in mind.
Excellent. Okay, Rafael, thank you very much. Congrats to you and to Christina and to the entire team. I enjoyed very much. Thank you.
Thank you. Thank you too. Thank you everyone. Thank you the P4 workshop for this opportunity to expose our work to the world.